Empirical correlations for free convection. Okay, so if you're a chemical engineering student, you know these correlations are, well, a lifesaver. They're how we quantify heat transfer when things get messy, like with turbulent flow, where trying to calculate it from scratch is pretty much impossible. So there are a few key things to get right. First, the core equation. It's the Nusselt number, which equals C times the Grashof number times the Prandtl number, all raised to the power of m. Now that product of Grashof and Prandtl, that's what we call the Rayleigh number. And here's a super important detail. All your fluid properties have to be evaluated at the film temperature, which is just the average of the surface and the surrounding temperatures. Second, what about those constants, C and m? Well, they aren't one size fits all. They completely depend on the geometry of your surface and the flow regime, whether it's laminar or turbulent. And that's because natural convection velocities are actually super slow, just a few hundred millimeters per second, making them really tough to measure precisely in a lab. So as the flow changes, your C and m values are going to change too. And finally, you've got to get the characteristic dimension right for your specific setup. For a vertical plate, you're going to use its height, L. For a horizontal cylinder, you'll use its diameter, D. You'll find yourself relying on comprehensive cables to look up the correct C and m values that correspond to your specific geometry and Rayleigh number range. So really, mastering these fundamental dimensionless groups and empirical forms gives you the essential toolkit for solving real-world natural convection problems. Let's dive into more detail.
Hey everyone! Today we're going to dive into something that's all around us, but we almost never think about it. It's this silent, invisible engine that's constantly moving huge amounts of heat. And once you see it, you'll see it everywhere. I mean, think about it. How does a radiator heat up a whole room? There's no fan, no moving parts. The hot air just seems to know where to go. Or what about that shimmering haze you see over a hot road in the summer? That's not just a mirage, it's a real physical process. So what's actually going on here?
Well, the answer to all of this is natural convection. You might also hear it called free convection. It's really just the movement of a fluid, like air or water, that's caused by density changes when you heat it up. You see, when fluid gets hot, it expands and becomes less dense, so it floats up. Then, the cooler, denser fluid sinks down to take its place. It gets heated, and the whole cycle starts all over again. It's this amazing, self-sustaining loop of energy.
Okay, so as engineers, it's one thing to get the concept, but it's a whole other game to actually calculate it. And a good rule of thumb in engineering is you can't solve what you can't see. So before we jump into the numbers, let's figure out how we can actually look at this invisible movement. Here's the tricky part. The speeds in natural convection are usually tiny. We're talking maybe a few centimeters per second. So you can't just stick a little windmill in there to measure it, because that would completely mess up the flow you're trying to study. So clever researchers came up with some brilliant ways to use light itself to see what's happening. And this is so cool. What you're looking at on the left is called an interferogram. Each of those fuzzy vertical lines is basically a line of constant temperature. See how they're all bunched up right next to that dark vertical plate? That tells you the temperature is changing really fast right there, and that's the engine driving this whole thing. Now, that temperature field makes the air move, and that's what you see on the right. That's the velocity profile. The air starts at zero speed far away, it gets heated, speeds up, hits a maximum velocity, and then kind of slows down again. So cool, right? We're literally seeing the cause and the effect side by side.
Oh, right. So we've seen it, now we need to be able to describe it with math. And to do that, engineers have this special language made up of what we call dimensionless numbers. Let's go ahead and build our toolkit with the 4 most important ones you'll need. First up, we've got the big one, the Grashof number. Think of this as the engine's power level. It's basically a tug of war between the buoyancy force, that's the force pushing the hot, light fluid up, and the viscous force, which is like the fluid's own internal friction trying to slow it down. If you have a big Grashof number, it means buoyancy is winning, big time, and you're going to get some really strong convection. Next, we've got the Prandtl number. Now this one is different. It's not about the situation, it's all about the fluid's personality. It compares how fast momentum spreads through the fluid versus how fast heat does. Think of it like this. In a liquid metal, which has a low Prandtl number, heat just zips through way faster than any motion spreads. For air, it's about 0.7, meaning they're a little more balanced.
So what happens when you put the last two together? You get the Rayleigh number. It's just Grashof times Prandtl. And this number is a game changer. It's the one that tells you what the flow is actually going to look like. Is it going to be nice, smooth, and predictable, which we call laminar? Or is it going to be a chaotic, swirling mess, which we call turbulent? For a vertical plate, the magic number is around 10 to the ninth. Below that, it's laminar. Above that, it gets wild. And finally, we have the number that's usually our whole goal, the prize at the end, the Nusselt number. This is our report card. It tells us how much better our heat transfer is with convection compared to what it would be if the fluid just sat still, which is called conduction. So a Nusselt number of 1 means you have no convection at all. A Nusselt number of 100 means convection is boosting your heat transfer by a factor of 100. So yeah, we always want a bigger Nusselt number. Okay, we've got all the pieces of our toolkit. So how do we actually put them together to solve a real problem? Well, it turns out that after decades of experiments, engineers found a kind of master key, a formula that connects everything together. And here it is. Now, I know it might look a little intense at first, but trust me, this equation is our best friend. Let's break it down. On the left, we've got NU, the Nusselt number. That's what we want to find. On the right, you see that GR times PR. Hey, we know that. That's just the Rayleigh number, RA. And that little F subscript on everything just means we need to get our fluid properties at something called the film temperature, which is just the average temperature between the hot surface and the cold air. Simple enough? So the whole thing is tied together by these two mystery constants, C and M. Right? That's the big question. We have this amazing master key, but where on earth did C and M come from? Did somebody just make them up? What's the deal with those? Well, they come from an engineer's cheat sheet. Basically, people did tons and tons of experiments and boiled all that data down into simple tables like this. Using it is super easy. First, you find the geometry of your problem. Are we talking about a flat plate or a round cylinder? Then you look at the Rayleigh number you calculated. Is it in the laminar range or the turbulent range? And boom, the table just tells you exactly which C and M values to use. It's the bridge from our specific problem to the master formula. All right, enough talk. We have the theory, we have the language, we have the master key, and we have the cheat sheet. It is time to get our hands dirty and actually solve a real problem, step by step. So, here's our setup. Picture this. We have a massive vertical plate, 4 meters high. That's probably taller than the ceiling in your room. It's heated up to a toasty 60 degrees Celsius, and it's just sitting in a room where the air is a pretty cool 10 degrees Celsius. Our job is to figure out exactly how much heat in watts is pouring off this plate into the air. And here's our game plan. It's the same reliable 6-step recipe every time. Step 1, find that film temperature so we know what our air is doing. Step 2, look up all the properties of air at that temperature from a table. Step 3, the big one, calculate the Rayleigh number. That tells us what the flow looks like. 4, take that Rayleigh number to our cheat sheet and find our C and M. 5, plug everything into the master formula to get our Nusselt number. And finally, step 6, use that Nusselt number to find the actual heat transfer in watts. Let's do it. Okay, so after we run the numbers, we find our film temperature is 35°C, we look up all the nerdy properties for air, we plug everything in, we get this. Our Rayleigh number is a whopping 2.62 times 10 to the 11th. So what does that giant number tell us? Well, remember that threshold for vertical plates was 10 to the 9th? We are way, way past that. This tells us our flow is definitely turbulent. And that tells us exactly which line to use on our cheat sheet, the one where C is 0.10 and M is 1/3. So we take those values for C and M, we take our huge Rayleigh number, and we plug them all into our master formula. That gives us our Nusselt number, and from there, it's just one more quick calculation to get our final answer, and drumroll please, 9,606 watts. Now, just to put that into perspective, that's over 9.6 kilowatts. That's like running 10 big space heaters at full blast. All of that energy is being moved without a single fan, just by this silent, invisible engine we've been talking about. And just like that, we've done it. I mean, think about what we just did. We started with something you can see any day, shimmering heat. We learned the language to describe it, and we used a simple toolkit to get a real precise number. That whole journey, from observation to calculation, that is the heart and soul of engineering. So from now on, when you see steam rising from a hot drink or feel the warmth from a radiator across the room, you'll know exactly what's going on under the hood. This process is everywhere, from cooling your laptop to designing buildings. You have the master key and you have the cheat sheet. So the only question left is, what mystery are you going to unlock next?